Okay, here's the good news about Newton's third law. There's no new formulas. Okay, there's nothing like mathematically new about Newton's third law. In fact, whenever you solve a Newton's third law problem, you actually use Newton's second law to do it. Okay, the only thing you have to know in order to recognize or solve a Newton's third law problem is that everything has a reaction. Okay, if I push on a wall, the wall pushes back. Okay, if you punch somebody in the face, their face punches your hand back. Okay, it's why you break your fingers in a fight. Okay, why you break your knuckles or break your hand. Okay, you can't exert a force for free. Okay, every time you exert a force, there's a force exerted back on you. It's equal and opposite. Okay, that's where Newton's third law comes from. Every action has an equal and opposite reaction. Okay, if that was not the case, things would not behave the way we understand them to behave. All right, the Earth would be a very weird place, right? Which is why Newton called the reactive force that he discovered the normal force. It kept things normal. Okay, without it, things would be weird. All right, things just would not work. All right, so things we have to understand. All forces act in pairs. Okay, that's the first thing we have to understand. Every action is equal and opposite reaction. So if there's a force, there's a reactive force. That's a reaction pair, action-reaction pair. Okay, so normal force is that reactive force. It's the force back on you, right? And understand that for every action, there's an equal and opposite reaction. The most often misquoted physical law there is. Okay, people quote this law all the time, and they use it completely out of context, especially when it is applied to like sociological situations. Like if I say something really awful to someone and they slap me in the face for it, oh, well, like every action has an equal opposite reaction. No, you said something totally offensive and someone slapped you in the face. That's hardly opposite of what should have happened. Okay, so don't try and apply this law to sociological situations. It does not apply there. That's that whole gray area thing. Not even like sociology is not really a science. Okay, all right. So with Newton's third law here, okay, like we said, there's action-reaction pairs. So if we're looking at a football game, okay, and the two lines are lined up, and the center, okay, puts the ball back to the quarterback, okay, and the two lines crash into one another, okay, they both feel that. Okay, when one exerts a force on the other, it exerts a force back. Okay, and so you hear, if you hit somebody in any sport, okay, like in hockey or something like that, right, you feel that force back, that reactive force. You can't crush them into the boards without feeling that push back on your own shoulder. Right, everybody kind of follow me there. All right. So they crash together, okay, but if you think about your opponent, they feel the force as well, okay? In other words, there's not just one force going on here, okay? And Newton was the first person to realize that all forces act in pairs. And in fact, this is the basis behind how rocket engines work, okay? All rocket engines use what we call, or all like spacefaring vehicles use what we call reaction control systems. And that is how they maneuver in space. Okay, so for example, back when the space shuttle was still flying, right, it looks like a plane, but do its wings work in space? No, there's no air, okay? Conventional airplane wings only work if there's air rushing over the top, creating lift. Okay, so as air rushes over the top of an airplane wing, the air on the top slows down, the air on the bottom, because of the shape of the wing, can go a little bit faster. If you move the flaps, okay, if you've ever been on a plane, you can see that the parts of the wing move. Okay, when they change the angle of the parts of the wing, they can create either a force upwards or a force downwards. Right. Same goes if you have like a car that has a big rear spoiler or a big wing on the back. Okay, it's creating a down force on the back wheels. Okay, in order to keep them in contact with the road as your speed increases. Obviously, on some cars, those are purely decorative. Okay, on other vehicles, they actually change the angle as the car goes faster. So if you have like really high-end car like a Ferrari, Porsche, Lamborghini, okay, they all have these little spoilers that pop out, okay, and change angles as you increase in speed, and that creates a reactive force that pushes down. Okay, so the spacecraft, they have to use these reaction control thrusters. All right, so there's pressurized gas inside of them. When they allow the pressurized gas to escape, okay, because it's under pressure in the tank is squeezing the gas. And so it's pushing the gas out. But as the gas is pushed out, it pushes back on the tank. And the person wearing the tank is then thrust forwards. All right, everyone kind of follow me on that. All right, I'm sure that when you were little, you probably saw this. Okay, so a reaction control thruster works in that way. We have this gas that is escaping. Okay, so when you were a kid and you played with a balloon, okay, you blew up the balloon, the gas inside is pushing on the inside of the balloon. The elastic nature of the balloon is pushing on the gas. As soon as you let it go, okay, they push on each other. There's a reaction pair that causes the balloon to fly all over the place within the room. Okay, because the balloon's opening is flexible, that's what makes it fly in all different directions. If it was fixed, then it would only go in one direction, okay, like a conventional rocket would. Okay, so I want you to consider this situation. You're somehow in this boat without a paddle, and you need to get to the dock. Could I run along the boat and jump onto the dock? Yes. It doesn't seem like it's right, but it's true. Okay, we all have this idea that if I ran on the boat would slip out from underneath me. Right? That's what we're all thinking, right? Because the boat's in the water. If I run on the boat will go that way. That's true. The boat will go that way. But the boat and I are not the same mass. Okay? And as long as I'm not pushing back so much on the boat, if I'm lifting my feet and getting to here, when I jump, if I don't push back too much, but push a little bit more down, am I going to be okay? Yeah, because if I push back, okay, I have to push a little bit back, yes, okay, but if I don't push too much back, the boat shouldn't slide out from underneath me, right? If I push a lot down, because I have to jump up onto the dock, right? Otherwise, I'm going to lose a lot of teeth. Okay, so I want to push down a bit and back a bit on the boat. But here's the thing: if I push down and back, it's not just the boat I'm pushing on; it's also all the water underneath it. Now, there's way more mass on the other end of that equation. If I'm just pushing backwards on the boat, you're right. It's just the mass of the boat, and the boat's going to slide backwards. But if I push a little bit more down, I bring in more mass. Michael, question? Well, yeah, I'm not saying that there aren't other forces that make this not as simple as I'm making it out to be, but okay, theoretically, you could do this. Okay, so here's what sets up. Newton's third law says that mass 1 times acceleration 1 equals negative mass 2 times acceleration 2. Okay, the two objects are an action-reaction pair. If I exert a force on the boat exerts the equal but opposite force back on me. Okay, so as you can see, this is still just Newton's second law, m times a equals m times a, right? So what I want to do is not just use the mass of the boat as the second mass, I want to use some of the water as well. Because if I can make this number really big, this number will be really small. Now, if I go over to here, this is my mass. It would be less than the mass of the boat and all the water underneath it. So my acceleration would be larger than the acceleration over here. It's only the forces that are equal, not the accelerations. Okay? The only time the accelerations would be equal would be if the masses were also equal. So as long as I can involve more mass by pushing downwards and involving the water, okay, then I can get a greater acceleration for myself off of the boat. Okay, everybody all right with that? Okay. So this would be a similar thing if you watched over the Olympics, they had all that pairs figure skating and stuff. Okay, you ever notice how there's like a massive difference in the size of the two skaters? Okay, like the female skater is always tiny, okay, and the male skater is usually quite a bit bigger. A lot of the spins and throws would not work if their masses were closer for a couple of reasons. First off, the guy has to be pretty strong to throw the girl around the way that they do, okay? But also, the accelerations and the forces that would be back on the larger person, if they weren't that large, their acceleration would be greater and it would be harder to control. So when they're doing that crazy thing where he's hanging onto her skates and swinging her around and around, okay, that wouldn't work nearly as well if their masses were closer, okay? Because then he would have a harder time balancing the force she's exerting pulling on him. He's pulling on her because she's pulling on him and trying to escape in a straight line, which if he lets her go, she eventually does. Okay, and then she like flies off and somehow lands. It's like crazy that no one ever gets killed doing that stuff. Okay, you guys kind of know what I'm talking about there? There's a lot of forces and reaction pairs involved in that. Okay, now I'm going to show you another one that's often one that's overlooked. How many people in here have ever fired a real gun before? Okay, what do you always have to be mindful of when you fire a real gun? Recoil. Yeah, you could break your shoulder if you don't do it right. Okay, and a lot of people don't do it right because they've watched action movies all their life and they see these guys that are holding guns away from their body and somehow not experiencing what really happens when you do that, because obviously they're firing blanks that have basically no kick. Okay, so firing a blank, incidentally, has basically no recoil. Firing a real bullet produces recoil. What happens is when you have any type of firearm, okay, and you detonate the powder, okay, the gases expand and they push on the bullet, but there's a seal, not a perfect seal, but basically a seal between the bullet and the barrel of the gun. So the gases push on the bullet, and what does the bullet do? It pushes back. That's what produces the recoil. Okay? It's actually the bullet pushing back on you. But there is so much force in there, that's why the bullet can accelerate so quickly, okay, that it will kick the gun back at you. All right? So if people like firing a rifle, if they don't have the butt against their shoulder, it will kick back into their shoulder, possibly break their collarbone, leave a big bruise, okay, and then usually rotates upwards, hits the shoulder and rotates up and gets them in the face. Okay, same thing happens with a pistol. Okay, you see guys in the movies doing this. It is incredibly hard to hold a large caliber handgun with one hand. Okay, and actually discharge it without it flying all over the place. Okay, that is why if you ever watch the people who know what they're doing, okay, it is a two-handed operation and it is braced. Okay, it's not held with straight arms, it's held and you lean into it a little bit, okay, in order to keep it from going all over, and it's still going to move. Okay, and obviously the larger the gun, the larger the bullet, the more recoil there's going to be. Firing a small caliber weapon doesn't produce nearly as much recoil as shooting something larger. All right, so I'm going to show you this one because it's funny. All right, so let's look at this example here. We have this spacecraft that has a mass of 11,000 kilograms, and there's an astronaut who has a mass of 92 kilograms, and he's going to push on the spacecraft. What's going to happen? Well, two things are going to happen. One might be quite small and almost not noticeable, and the other would be a bit more noticeable. But two things are going to happen. Yep, unless he has like a thruster pack on. Okay, he'll be pretty much screwed because he's going to accelerate away from the spacecraft, and the spacecraft is also going to accelerate away from him. Okay, so when the astronaut pushes, they both accelerate because he pushes and causes an acceleration, but the spacecraft pushes back according to Newton's third law with an equal amount of force. This is where people run into trouble in terms of perception. They watch what happens and they see that the spacecraft hardly moves and the astronaut flies backwards. And they assume there was more force on the astronaut. But the forces are equal. Okay, that's the thing people don't often realize. They see the result of the force, they see the acceleration, but they don't realize that that was actually produced by equal forces. All right, so if we set this up, okay, we're going to say that the force of the, oh, that's not a good color to use, sorry. We're going to say that the force of the astronaut, okay, is equal to negative the force on the spaceship. Okay, they're equal, but they're opposite. So I should be able to find the acceleration, okay, of both the spacecraft and the astronaut. I don't actually have to solve it this way. I can now treat them separately. So the force on the astronaut is equal to the mass of the astronaut times the acceleration of the astronaut. The force on the spacecraft is equal to the mass of the spacecraft times the acceleration of the spacecraft. Okay? Since I have all those numbers, okay, I should be able to calculate, okay, the acceleration of both, okay, because I know this was the force. So on the spacecraft, the force is positive. On the astronaut, that force is negative because he's going to go backwards. All right, so in this case, I have negative 36 newtons equals 92 times the acceleration of the astronaut. And then over here, I've got positive 36 newtons equals 11,000 kilograms times the acceleration of the spacecraft. Okay, I can solve now for those two accelerations because I've realized the forces were equal. That's the only thing I have to realize in order to solve this. Okay, so when I divide negative 36 by 92 kilograms, okay, I'm going to get the acceleration of the astronaut. Oh, not the times divided. All right, so the astronaut is going to accelerate at 0.39 meters per second squared, which doesn't seem like very much, and it's not, but if you have no way to get back to the spacecraft, it doesn't matter how small it is, okay, you're pretty much screwed. Now, how long is that acceleration going to occur for? Right, as long as he's pushing on the spacecraft. As soon as he loses contact with the spacecraft, now he's just going to what? Float away, but at a constant speed or accelerating? Constant speed. Now the force is gone, right? He's not pushing on anything anymore. Now he just moves at a constant speed. Okay, so not very fast. He's not going to be going very fast because that acceleration was small and only lasted for a few seconds. Well, probably not even a few seconds. Okay, now the acceleration on the spacecraft, okay, is going to be 36 divided by 11,000. All right, so considerably smaller. Okay. Now, we may look at that number and go, oh, that number doesn't really matter. But if you are working at like the Jet Propulsion Laboratory and you are trying to get a spacecraft to a distant object like the New Horizons probe when it went past Pluto and now it's going to some other Kuiper Belt object, it's going to meet up with it in like January, okay? That small acceleration, even for a small amount of time, could be cause for a course correction. Okay? That represents that the spacecraft has been pushed off of its original course. Okay? And even a small angle, if it's allowed to continue, okay, over a huge distance, can make a pretty big triangle, right? If we're looking at something like this, let's say, okay, so here would be a straight path, and that acceleration produced just a slight deflection. Okay, well, that angle's not very big, but the farther I go, the further off from my target I'm going to be, even if it's a very small angle. When we're talking about astronomical distances, a small angle can mean you missed the whole planet by a really long way, right? And that would be bad. Okay. All right, is that making some sense? That's a pretty simple one, but okay, that's how they work. Okay, so that's what we just did. All right, so action-reaction situations are responsible for all things that essentially we use in real life. If it wasn't for action-reaction, we wouldn't be able to walk. Okay, the only reason I can propel myself forwards is because I'm pushing the Earth backwards. Okay, I push back on the Earth and the Earth pushes me forwards. Okay, Nike has this commercial out right now that's like a total farce. They have everybody running at the same time because the Earth has stopped spinning. So they figure if they get everybody to run at the same time, they'll get the Earth spinning again. First off, the Earth's not going to stop spinning. Secondly, that's stupid. Okay, and as soon as I saw that ad, I lost it. I'm like, God, see, just more examples of people being convinced of things that can't happen. And then my wife goes, I'm leaving because she can't stand it when I start arguing physics with the television. I don't do that all that often. Okay, so anyway, they've got this terrible commercial that implies that somehow the people can change the movement of the Earth. We can't. We're actually going to do an activity on that after Easter that'll mathematically prove that it can't happen. Okay, and then when you see that Nike commercial, you'll be as frustrated as me. That's what we're going to do, actually, is we're going to see what would happen if everybody on Earth jumped at the same time in the same place, which would be physically impossible, but we'll say it could happen. What's that? No. Okay. So because of the mass of the Earth, when I walk, I don't do anything to the Earth. In fact, it's more likely that I, slightly deform the floor or whatever than I would actually move the Earth. Okay. Now we did talk about when you jump, you're using Newton's third law. If I want to leave the floor, I have to make the floor push harder on me. So I push harder on the floor. Okay. I bend my knees and I exert a harder force against the floor, and that propels me up off the floor. Okay. All right, another application of Newton's third law. I'm sure you've all seen the crazy people who like rent a U-Haul trailer, tow it behind some incredibly small car that shouldn't be towed behind, okay? And they travel down the Deerfoot at 130, completely ignoring the giant sign on the wheel well that says maximum speed 80 kilometers per hour, okay? But they do it because people are silly, okay? Anyway, inside of those small U-Haul trailers is a Newton's third law, or a reaction control braking system. Okay? Most of the small cars that are pulling those U-Haul trailers do not have an electronic brake harness, okay? Which means there's no way to run electrically powered brakes on the trailer from the car because there's no way to hook them up. Okay? Not all cars have that. Most trucks have a little plug on the back that you can plug trailer brakes into. Also operates the lights and things like that. Okay? Well, for these, there's no way to do that. So they have a small battery that operates the lights, and they have a switch in this actuating mechanism. So this actuating mechanism is attached to the hitch receiver, okay, the part that fits over the ball. All right, so it goes over the ball, and there's a spring-loaded mechanism in there. If the car in front starts to slow down, the trailer wants to continue to travel forwards according to Newton's first law. But when it does, it pushes on the car. Everyone follow? Okay. If it pushes on the car, what does the car have to do? It pushes back. And that push back pushes in on the spring, which applies the brakes on the trailer. So it actually uses the fact that if it tries to travel forwards, the car will push back on it, and that will activate the brakes, which is fine if you're driving it in a sensible fashion and slowing down slowly. The problem is if you have to perform some sort of emergency maneuver, like you have to slam on the brakes, okay, basically it doesn't get a chance to actuate because the trailer then tries to pass the car because it rotates around the trailer ball. Okay, if you hit the brakes really, really fast, the trailer will come forward and rotate around the hitch in doing something we call jackknifing. Okay. Okay, we call it jackknifing because when a big semi-trailer does it, it actually looks like a partially opened pocket knife. Okay, it'll actually come right back around. I once saw on Highway 22 a guy's boat come around and knock him off the road. Okay, he slammed on the brakes because a deer ran across the road in front of him, and the trailer came back around, hit the side of the truck that was towing it, and put them both in the ditch. Okay, he was going way too fast because I was going 115 and he flew by me like I was standing still towing his boat. Okay, yeah. Okay. So be sensible when you're towing a trailer. Don't go so fast. It's kind of a lot of mass there. Okay. So we're going to go over a few problems here and kind of see how we do. We've actually already solved a few Newton's third law problems. Okay, we had the series of boxes that were being pulled. We talked about them in terms of systems. Okay, but that was also a Newton's third law question. When the first box pulls on the back box pulled back, and we were able to calculate the tension in the rope that was connecting them. All right, so questions like that are Newton's third law questions, even though we didn't know it at the time. All right, so let's look at this one first. So I've got these three boxes, okay, and they're positioned next to each other on a horizontal frictionless surface. So there's no friction, okay? An applied force on box A causes all of the boxes to accelerate at 1.5 meters per second squared to the right. Calculate the force exerted by box C on box B. Okay, do I want to solve this as an entire system, or do I want to break this down into individual boxes? individual boxes. There is a system thing I'm going to use here, but I'm not going to use the whole system, okay? Because it doesn't make sense. I'm only looking for one force, and it's the force of box C back on box B. So which box should I use, B or C, to find this force? C. Why do I want to use box C? How many forces are acting on box C? One. There's only one force acting on box C. What is it? The force from box B. The only pushing it, right? What's pushing box C is box B, pushing it forwards. And whatever force B exerts on C is what C exerts back on B. Is that the force the question wants us to find? It is. Okay. It's a Newton's second law problem, but there's a lot of convoluted reasoning that gets us there. Okay. So I'm going to draw a free body diagram for box C. Okay. It's 5 kilograms. The only force acting on box C is box B. Okay? And because we understand Newton's third law, we know that that force is equal to the force C will exert back on B. All right. How am I going to find this force? Mass times acceleration. It's the only force acting on this box. Therefore, it's the net force. It's the only one. Okay? So I can solve for it by going mass times acceleration. They told me that all the boxes accelerate at this rate. So I can take the 5, multiply it by 1.5, and I'll get 7.5 newtons backwards. Okay, that's the force of C on B. Obviously, the force of B on C is forward. Okay. How much math was in that question? Hardly any, right? I had to do M times A. How much thinking did I have to do to get there? A lot, right? There's a lot of reasoning that goes into getting to that. Okay? That's what makes this unit tricky, is all the intuitive stuff that has to happen first. Okay, everyone kind of follow what we did there. All right. So, same situation, okay? So remember that the acceleration, we were told, was 1.5 meters per second squared. Okay, so for the situation in the previous example, we want to find the force that B exerts back on A. So we also had a force, applied force. No, they didn't tell us what it was. Okay. So let's see if we can find that. Yeah. Okay, I'm going to give you guys a few minutes on that one. Okay, and remember also that we calculated this force in that question as well. Okay, so the force of C on B was 7.5 newtons backwards. Okay, that's another piece of information that you'll want to use in this. Okay, remember there's no friction. Okay, see if you can figure it out. I'll give you one more hint. Only use one box to do it. Don't use the system, just one box. Okay, so your best bet in solving this, in fact, your only bet in solving this, is to use box B. Okay, they tell us that there's an applied force on A, but they don't tell us what it is. And so as a result, I can't use box A to find anything because I don't have enough information about box A. However, that situation is not true for box B. Okay, what's pushing this way on box B? This is box C. Okay, because we already established that in the last question. That's the force C exerts back on B. Okay, and we know that that is 7.5 newtons. So what's this force? Which box is pushing that way? A. Yeah, this is the force of A on B. The question wants to know the force that B exerts back on A, right? Wouldn't they be equal? If box A exerts this force on box B has to exert an equal but opposite force back on A. Everybody all right with that? Okay, that's the realization I have to come to if I'm going to solve this problem. So I know this force, and I can calculate the net force on box B because I know box B's acceleration. Okay, so the net force acting on box B is going to be mass times acceleration, so 10 times 1.5. The net force on box B is 15 newtons to the right. There are only two forces acting on box B. Everybody okay with that? All right, so if that's the case, then I can solve for the one I don't know, because the net force is going to equal force C plus force A. Right? So I'm going to subtract force C over to this side. Okay, so I'm going to have 15 newtons minus negative 7.5 newtons equals force A. All right, so the force of A on B is 22 newtons to the right. So the force of B on A is 22 newtons to the left. All right, again, it's all Newton's second law in terms of the arithmetic you have to do. Okay, but it's all the relationships you have to see in the question, okay, that really make these tricky. Okay, questions on that one? Okay, same idea. Now there's friction. Okay, now friction is involved. So A and B are made of identical material, okay, but have different mass. They're placed next to each other on a horizontal rough surface. Okay, an applied force acting on A causes both boxes to accelerate at 2.6 meters per second squared to the right. The magnitude of the force of friction on box B is 28.3 newtons. Calculate the force exerted by box B on box A. Okay, I want to have you try this, but which box should you use to solve it, A or B? Which one do you know the most information about? B. Yeah, it doesn't tell you what the force of friction on A is. As a result, you wouldn't be able to use the net force to calculate it on A, but you can on B. All right, so see if you can figure it out using box B. All right, so as we said, we want to start with box B because we know more information about it. Okay, we know it's 8.5 kilograms. Okay, and we know it's being pushed this way by box A, and we know that friction is resisting, okay, with 28.3 newtons. Okay. So there's what we have. We also know that the acceleration of box B is 2.6 meters per second squared. So can I find the net force on box B? Can I go M times A? All right. So F net equals 8.5 times 2.6. All right, so the net force on box B is 22.1 newtons. And that would be to the right. Okay, now I should be able to find the force I'm missing using sum of all forces, because the net force on box B is the force of box A plus the force of friction. So net force minus the force of friction should give me the force of box A. Okay, so that'll be 22.1 minus negative 28.3. Okay. All right, so 50, and we only have two significant digits here, so 50 newtons forward is the force of A on B. What's the force of B back on A? 50 newtons backwards. Okay, are these all working pretty much the same? Okay, we usually have to isolate one of the parts, okay, figure out the net force on it, and then find whatever force we're missing. Okay, but every one we've done has worked pretty much the same. All right, couple of reminders here, guys. Your lab reports are due, but not until obviously after Easter break. But if you want them, if you got any questions on them, probably best to come and see me before Easter break. Okay. Your unit exam will probably be not the week after the break, but middle of the week after that. Okay, so try not to forget everything. Okay, that is, have a look at a few things over the Easter break as well, okay, in preparation.